Hello everyone, welcome back to Physics 40C. Today we're going to be taking our second look at capacitors and then doing a brief introduction to current. So if we recall from lecture in the last video, capacitors are electrical components and we see them a lot in electrical circuits. And so it's important to start understanding how we use them in electrical circuits and the different ways that they can be integrated. So capacitors can be connected in either parallel or series with each other. And so what a parallel circuit would look like would be capacitors connected one after the other where they are facing parallel with each other. So if we drew those two lines, these two lines here are parallel. And so if there were, say, current to flow through this circuit, there is a break at the joint here. And so this break at the joint is basically where we see, okay, that's a parallel circuit. If a path can conceivably be drawn through one of the capacitors and not the other. With a series connection, the capacitors are joined up one after the other. So you have, say, a line here, another capacitor here, and then a line here. And this is to basically illustrate that there is no way for a path to be drawn through, say, this first capacitor that doesn't also go through the next two capacitors. And so one thing that I really wanted to illustrate, just to make it super clear, is you can't always depend on the shape just to determine what is in series and parallel. Sometimes you have to really look at the path that you take, because while we would say, oh yes, those two circuits that I just drew here, or those two capacitors are in parallel with each other, or they're kind of similar to this circuit that I drew over here, you still cannot draw a path through one of them that does not then flow through the other. So you do have to take into consideration the flow and through which components that the current is flowing. So for parallel, we will say the equivalent capacitance for a parallel, we can just use this sign, is going to be C1 plus C2 plus all of the other capacitors that might be wired in this way. So when they're in parallel, this is the equivalent capacitance formula that we use. With series, we think of the capacitance as compounding inversely. So what that means is 1 over C1 plus 1 over C2 plus dot, dot, dot. And so these are the two formulas that we use to combine multiple capacitors into a singular equivalent capacitor. Definitely more information in the lecture videos. He goes into it a lot more detail, and we can also go through it in session if you have any questions. So one of the more interesting or really critical things to know about capacitors is that the term capacitance refers to the capacity of the component to store energy. And so this is really important principle of capacitors, because we'll learn a few more different circuit components in the coming weeks, but this is the only circuit component that really serves this that really serves this purpose, and it's to store energy. So we tend to think of the energy that can be stored in a capacitor as being equal to Q squared over 2C plus, or sorry, and that can also then be equal to 1/2 C delta V squared. And so the units of this equation break down to just be equal to joules. And so this is joules of stored energy, or capacity. No, sorry, max capacity of energy. And so remember the units for capacitance, which is this C value is in farads, and this would be in coulombs. So it's safe to say that the units of coulombs squared over farads, similar to how this situation transpires, is equal to joules. And so after we really understand, or at least just know to use this equation for energy, we can start looking at circuits as a whole. And so I wanted to do a really quick intro to circuits and really to the main component of circuits, which is current. So current is the flow of charged particles, usually along a wire. So it's important to notice that these charged particles are most commonly electrons, because I've mentioned before that the other charged particle that we know of, protons, typically don't move because they change the structure of the atom that they're in. So we usually, especially with circuits, think of current and charge flow being electrons moving from place to place. So just a few key things to keep in mind as we learn more about current. So current is driven by uneven charge distribution. If an object or a circuit does not have an uneven charge distribution, there can be no current flowing. And so that is why we typically see, so if there were a perhaps battery and a capacitor, and say this was 1.5 volts here, the positive side and the negative side, the positive side of the capacitor has a voltage of 1.5 volts, and then at the back end of the capacitor, the opposite side would have a charge of 0 volts. And so this uneven charge distribution is what creates this current flow. And so the interesting part about capacitors now is because they can store energy, a circuit with just a capacitor in it, as long as the capacitor is charged, can also still maintain a current flow because there is an uneven distribution of charge. So the last thing that Professor talked about was the concept of drift velocity. Which actually, before I forget, I wanted to make an analogy because this uneven charge distribution, for me, it tends to make me think of, I don't know if any of you remember osmosis when you were studying in either chemistry or another physics class. Basically, it's the concept that, say, a salted water or a highly concentrate within water will flow from an area of high concentration to low concentration, and that this is driven by random molecular motion. Pretty much the same thing is what happens with current. There is an uneven distribution of electrons, and so the electron motion, which happens very, very quickly, is what creates this current. So current is driven by bulk motion. So while the electrons themselves are moving very, very fast in all different directions all the time, they're definitely more, I would say, moving even faster than vibration, because our eyes wouldn't be able to tell it, but definitely moving more towards vibration than just random bouncing. But the only time current is detected is when we get what's called bulk motion. So that means all of these rapidly moving random direction electrons need to have some kind of transfer over a threshold. And so this drift velocity is really slow. It's often about 1 or 0.1 millimeters per second. And so we wonder, okay, why do lights turn on then as soon as we flip a switch if this actual drift velocity, or really the thing driving the current, is so slow? Well, it's because, like water in a pipe, electrons are always present in the wire that it's in. So the minute that you turn on this switch and you're driving this current, you are asking the electrons that are already right near this light or whatever appliance you're trying to use to cross the threshold, which happens instantaneously, and then it continues happening forward. So that is going to be all the time that I have to cover just the basics of what we're going to be talking about in terms of current. If you have any questions, you can go ahead and leave them in the comments, or drop by one of the SI sessions, and the description will have all the details for that. Thank you. See you guys soon.